Hello, Luke. Welcome to lesson 48. So today we're going to be talking about polynomials, which means that today we will be spending a lot of time with definitions. So if you don't have your algebra notebook handy, get it handy and get it ready to go because there will be some writing in today's class. There's not going to be a whole lot of math. It's more all about understanding definitions for different expressions in math. So let's get started. To begin with, just a quick review. Just going to throw some expressions out here. So let's say if I have maybe an expression like this, or maybe I have an expression like this. All right, so these are all expressions that we've been dealing with. Maybe just throw a couple negatives in here just for fun, that we've been dealing with throughout the year. All right, so we've been seeing some of these, and we've been just calling them expressions and terms. Now, in algebra, there are a couple of kinds of expressions or kinds of terms that come up a lot, and it's nice to kind of have a name for them. So that we can distinguish them from other terms that we might use and other expressions that we might use. So that's what we're going to be talking about today. We're going to be talking about polynomials. Okay, so some of these that I've listed here are considered polynomials, others are not. All right, and all it is, it's just a terminology. So that's all we're doing, is we're just learning some new terminology so that when we express ourselves mathematically later on, you'll be able to understand what's being referred to. So let's talk about what a polynomial is. Let's just jump right to the definitions here. So what is a polynomial? A polynomial, right here, and I put in parentheses just to clarify that we're talking about polynomials in one variable. That's pretty much all we're going to be talking about right now. Later on, we might talk about polynomials in 2 variables or in 3 variables and so on and so forth. But in general, just think of it as in terms of one variable right now. So a polynomial is one term or a sum of individual terms, each of which is of the form, and I'm going to put the form right here. The form is ax raised to the n. Okay, now this seems really complicated, but it's really not. It's just a way of visualizing what a polynomial would look like. So this form, the a that we see here, that's a number. We just don't know what number it is. So we write it as an a. But the a is a real number. It has to be a real number. Okay. The x, that's the variable. That's the unknown. The n has to be a whole number, which, if you remember your set of whole numbers, it's essentially the set of positive integers including 0. So it would be 0, 1, 2, 3, on forever. These are your whole numbers. So this n has to be a whole number, which means it's a positive integer or the number 0. Okay? So anything that we can write in this form would be considered a polynomial. So let's say for the a here, let's plug in a real number. Let's plug in the number 4. And then we have our variable x. And then our n, it has to be a whole number. So we'll just say 4x squared. This is a polynomial. Check. It satisfies all the conditions. It's one term in this case, and it's of the form ax to the n, where a is a real number, x is a variable, and the n is a whole number, a positive integer. Okay, so this would be a polynomial. All right, another example of a polynomial might be, 7x to the 4th. This would be a polynomial for the same reasons that this one is. It satisfies all the conditions. All right, another one might be 1/2 x to the 3rd. All right, this looks a little bit different because we have a fraction in there, but this fraction is still a real number. So remember this fraction part here, that stands for the a. So that is a real number, which does satisfy the condition of a polynomial. So that works. We still have a variable, and we still have our positive whole number for the exponent. Okay, so this would also be a polynomial. All right, now let's look at some examples of things that are not polynomials. So if I have something that looks like this, perhaps, if I have 3 x raised to the negative 2, all right, this would not be a polynomial. And why? Think about it for a second and see if you can answer it. Why would this not be a polynomial? Well, hopefully you figured it out. The reason this is not a polynomial is because we have a negative exponent. And the exponent, which is the n, has to be a whole number. And a negative 2 is not a whole number. It's outside of the whole number set. The whole number set includes just positive integers and the number 0, not negative numbers. So this would not be a polynomial. All right? Let's try another one. What about 2x squared over 3z? Again, this would not be a polynomial. Why not? Well, because it's not in the correct form. All right? We don't have an a times an x raised to the n. We don't have that here. We have, a 2 times an x raised to a 2, but all of that's being divided by a 3z. So this is the incorrect form. So this would not be a polynomial. All right? How about, let's see here. What's another good example that I could give you? What about 1 over x squared? Okay. Would this be a polynomial? And again, the answer is no, because it's, again, not in the correct form. The x squared is in the denominator, and this doesn't say anything about the x squared being in the denominator. So no, this would not be a polynomial. Okay? How about, let's try some here and see if you can decide. What about if I have negative 1.4z to the third? Would this be a polynomial? Well, the answer is yes, it would be. We have a real number here. Real numbers can be negative, and it's being raised to a whole number. So that works out. That would be a polynomial. Okay. How about this one? Let's try, how about just, how about this? Is this a polynomial? Just a w, a variable. The answer is yes, actually, it is. All right, and you might say, but wait a minute, Jim, it's not in this form. I don't even see an a here, and I don't see an n here. Well, actually, they are there. They're just invisible, right? What's the invisible coefficient of a variable? It's 1. So there is a 1 hiding right there. And if we don't have any power designated, what is the invisible power? It's just a 1, right? So we could rewrite that w as a 1w to raise to the 1. And if we do that, we see clearly that, hey, we do have an a, we do have a coefficient here of 1, and we do have a n, we do have a power of 1, and 1 is certainly within the whole number set. So therefore, this is a polynomial. So it's a very simple polynomial, but it is a polynomial. All right? What about this one? What about the number 4? Is that a polynomial? All right, well, the answer is yes, it is. Okay, and why is it? Well, kind of for the same reasons that the w is a polynomial. All right, let's try to get this into the form that's needed. All right, so if a is kind of the coefficient, well, we already have the coefficient. That's a 4. That's easy. All right, we don't have a variable. That's a problem. But we could say that there's an invisible variable here. Okay, it's an x, let's say. But in order for it to be invisible, it'd have to be equivalent to 1, because 4 times 1 is just 4. So how can we make x, no matter what x is, equal to a 1? Well, let's raise it to a 0, right? because if you recall, anything except for the number 0 raised to the 0 power is always going to be 1, right? If I have an x to the 0, well, that's equal to 1. If I have x, y, z all raised to 0, that's going to be a 1. If I have a 203 raised to the 0, that's going to be a 1. So anything raised to the 0, so long as it's not a 0, is going to equal 1. So x to the 0 is equivalent to a 1. And so 4 times 1 is just 4. So it doesn't change anything by thinking of this as having an invisible x to the 0. All right, and if it's written as 4 times x to the 0, now we're actually in the proper form. We have a coefficient, which is a real number, the 4. We have a variable, an x, and we have a whole number, integer, which is the 0 that is in the whole number set. So this would be a polynomial. All right, so even though the word polynomial sounds rather intimidating, it's really a simple idea. Okay, it's a very simplistic algebraic term. It's almost as simple as you can get. It's just a single number, or it's just a single number with a variable raised to a positive exponent or a 0 exponent. All right, which actually brings me to it. Yeah, I mean, if we had anything with a 0 exponent, so if we had, the number or the variable w0 raised to the 0, that would also be a polynomial. Okay, it is equivalent to 1, but it would be a polynomial because we have this invisible coefficient, and we are raising it to a 0. So that would also be a polynomial. So don't be afraid when they say polynomial. You should actually be kind of happy when they say this problem will only deal with polynomials, because the polynomial is about the simplest algebraic term that you can get. It's a good thing. All right. So that is what a polynomial is. Make sure you've got this definition along with the form written in your class notebook so that you can study that and memorize it. And if you want to pause the video right now and do that, you certainly can if you haven't done it already. Otherwise, we're going to continue on, and we're going to start talking about a binomial. Okay, so we've talked about the polynomial. Well, let's talk about the binomial. All right, and that actually brings us back to the definition of the polynomial, because we've actually only gone over half of the definition. The definition says that it is either one term or it's a sum of individual terms. So we've talked about the one term. All of these would be just one terms. We haven't really talked about the sum of the individual terms. So that's the next thing we're going to talk about. So if we have a sum of individual polynomial terms, what would that look like? Well, pretty simple. Let's just write down a couple of polynomials. Let's put in a 3x squared. That's a polynomial. And we're going to add that with another polynomial. Let's go with a 4z to the third. All right. So we have two polynomials. Clearly, both of these terms fall into the form and the conditions of a polynomial. So they're both polynomials, and we're adding them together. So this whole expression would be considered a polynomial expression, or just simply a polynomial. Okay, that's what we mean up here when we say a sum of individual terms. So we have individual terms that are polynomials, and we're adding them together, so this whole thing would be considered a polynomial. Okay, now that brings us to the definition of a binomial. A binomial is simply when there is only two terms. Remember, the word, or the syllable bi usually refers to two. We see that all the time. It's from the Latin, I believe, which means two. All right, so binomial would mean two terms. Okay, bicycle means two wheels on your bicycle or your bike. All right, biannual, it means twice a year. So anytime you see that word bi as a syllable, it usually means the word two. So if we have a binomial, it just means we have two terms that are being added together, and both of those terms are polynomials. So you could look at this and you could say, oh, this whole expression is a polynomial, But if I wanted to be even more precise, I could say this whole expression is actually a binomial. Okay? Either one would be correct, but binomial is the more specific definition for what this is. Okay, good. So that's all there is to it. That is a binomial. So this would also be a binomial. Okay, because remember, a 3 is a polynomial and a 4 is a polynomial. So we're combining two of them, so that would be considered a binomial. Now, if we were to simplify it, we could say that that equals 7, and 7 is just all by itself. That would just be a polynomial. This would not be a binomial, but this side would be a binomial. Okay? All right. So let's continue on to the next step here, and make sure you have this written down in your class notebook as well. Let's talk about what a trinomial is. Okay. Well, take one guess. What's a trinomial? I think you probably got it. A trinomial is simply where we have three polynomials being added together. So let's say I have a 3 plus a 4x to the third minus, let's go with a x to the second. All right. So here we have three terms. Each of these terms, if we look at them individually, they each are polynomials. All right, we could put all three of them into the form that we need to, which is the ax to the n. We can put all three of these into that form, so they are polynomials. Therefore, we can count them up. So there are 1, 2, 3 of them, so we're going to call it a trinomial. And just like bi means 2, tri means 3. Okay, so it's a 3-term polynomial. And again, you could call this a polynomial, which is kind of the broader definition of it. Or you could call it a trinomial, because there are three of them. Okay? It's as simple as that. And that's why I said this class is really based on, or is really all about definitions. So write that one down in your class notebook, and we'll move on. So next we're going to talk about the degree of a term. So when we have a term, and this is, well, we'll restrict ourselves to just polynomials still. So if we have a polynomial and we want to know the degree of it, okay, the degree of a term, let's give us a term here. Let's give us 2xy. The degree of the term is the sum of the exponents for the variables within the term. Okay, so we have this term, 2xy. This x has an exponent of 1. This y has an exponent of 1. The sum of all those exponents is 2. So this is a 2-degree term. It's a 2-degree term because the exponents would all add to 1. All right, it's just a way of describing it. We don't really do anything mathematically per se with this, but we just are able to describe this term as a 2-degree term, again, for the reasons that the exponents add up to a 2. So if I have maybe something like this, 3x to the third, y to the fifth, okay, what degree term would this be? Well, it would be an 8-degree term, right? Because the exponents all added together give us an 8. Notice we don't need to have, like variables. We're not actually multiplying this or adding this. We're just, again, using this as a way to describe these terms. So mathematically, we're not really doing anything. We're just adding up the variables and describing it, or adding up the exponents and describing it as that many degree term. Okay? So what would the term, or the degree for this term be? How about a 3? What would the degree of this term be? Well, hopefully you looked at it and said this is of degree 11, right? Because I have a 2 plus, don't forget this 1 that's invisible here, plus this 3, and then plus the 5. That's 3, 6, 5 is 11. So that would be an 11-degree term, or of degree 11. All right, so that is how you find the degree of a term. Pretty straightforward. Now, how do you find the degree of the polynomial? Now, because remember, a polynomial may have more than one term in it. If it's just a single term, it's no different than what we have up here. These are all polynomials that I've used up here as my examples. So the degree of this polynomial is still 2. The degree of this polynomial is still 8. But polynomials aren't restricted to just single terms. We can have, as we said earlier, we can have several of them being added together. So if I have the binomial 3x squared y to the third, and I'm adding that with maybe 12 x to the fourth y, okay? This is a binomial. What is the degree of this whole binomial? Not just the individual terms. What's the degree of this whole binomial? And the answer is the degree is always going to be the same as the term of the highest degree within the polynomial. So we look at the degrees of the individual terms, and we say, okay, this one here, go to a different color. This one here has a degree of 5. This one here has a degree of, oh, actually, I didn't look at this before I did it. We're going to change this, make it y to the second. That way we have one that's more than the other. So this one has a degree of 6, right? If we add the exponents. So what degree is this whole thing? Well, we go to the term with the highest degree, and we use that degree. So the highest degree term here is a 6th-degree term. So we would say the whole polynomial has a degree of 6. So this would be a 6th-degree polynomial. Or you could say a 6th-degree binomial. That would be also good. All right, let's try another one. What if we've got 2x to the third plus 4 plus 5x squared y squared plus z squared. Whoops, not z to the 0, z to the third, we'll say, plus 4x squared. So what is the degree of this polynomial? And we might even ask, well, yeah, this polynomial. Looking at it, let's add up all the degrees. So the degrees of the first term, I'm sorry, not add up all the degrees. Let's look at the degrees of each of the terms. So the degree of the first term is going to be what? It's just going to be a 3, right? That's the adding of all of those exponents is just a 3. Now this is an interesting one because it doesn't have a variable. It is still a polynomial, but it doesn't have a visible variable. But it does have an invisible one, and we'll call it an x to the 0. Okay, so what would be the degree of this term? Well, the degree on that one is going to be a 0, right? Because that's the sum of all the exponents of the variables. So it's a 0-degree polynomial. Here we have 4. And then lastly, for our z, we have a 3. Well, actually, not lastly. For our z, we have 3. For our x, can't forget him, we have a degree of 2. So what is the degree of this whole expression, this whole polynomial? Well, we look at the term with the highest degree. And the highest degree is this one. It's a 4. So this one has, as a whole, a degree of 4. Okay? Hopefully that makes sense. Excellent. All right, let's move on and talk just for a minute here about how to simplify polynomials. So when we're simplifying polynomials, there's really 2 steps in it. One step is something that we've been doing for a long time now and should be very easy review. The second step is just a kind of a way of organizing our answer. So the first step, well, actually first let's give ourselves a polynomial. So let's say we have yeah, we'll leave it like that. So we have a great big polynomial, which, by the way, we talked about binomials, trinomials. After that, if there's 4 terms, or in this case, there's 5 terms, we just call them a polynomial. There isn't any specific term that we give something that has more than 3 terms. All right, so we just call this a polynomial. And the first step in simplifying it is to combine like terms. All right, pretty straightforward. That's something we've been doing all along. So where do we see like terms here? Well, we see an x squared here and an x squared here. So those two would be like terms. So we can combine them. That's going to give us 11x squared, right? And then we might say, well, I also see a 3y here and a 6y here. Those are like terms. We can combine those, and that's going to give us, I'll keep the same color here. That's going to give us 9y. And then finally, we have what's left over. We just have this positive 4x term, so we'll tack him on at the end, like so. All right, and now we've simplified it. That's as easy as it gets right there. We've just combined our like terms. That's step one, okay? Now what's step two? Step two is just kind of, again, a way of organizing your answer. So once you've reached this point, the thing to do is to rewrite it so that it is in descending powers of the variable. Descending powers of the variable. Now, in an expression like this that has multiple variables, we just select one. Usually we'll select the variable with the largest exponent. So in this case, the largest exponent is a 2, and the variable for that is an x. So we will then rewrite this problem, organizing or rearranging the terms so that the x powers are ordered from largest to smallest. Okay, so the x power of 2, that's the biggest one, the largest one, so we're going to write that term first. That actually doesn't change. But then we're going to go and we're going to put this 4x next, okay, because that's the next power for x. We go from an x to the 2 to x to the 1. So we're going to put that next as a positive 4x. And then we're left with this positive 9y, which you might even think of it as being 9y. You know, if we need to force ourselves to put an x in there, we could put an x to the 0 because that just means 1, which doesn't change the value. So you can see then how we went from a 2 to a 1 to a 0 with our x's here. All right. Now you don't need to obviously write that x to the 0, but just you can think of it that way. All right, so there we have, and I'll erase the 1 too because that's understood. There we have our answer expressed in kind of a proper way with the greatest power for the variable at the beginning, and then we step down to the lowest power at the end. So this is not mathematical in the sense that we're not changing anything. All we're doing is rewriting the problem. So really the steps would include combine the like terms, and then we're just, step number 2 is just rewriting the problem, only in a nicer way. Okay, so that is how you would simplify polynomials. So let's just go through here and do a couple. I think actually I'll probably just pull a couple out of the book here so that I make sure that these are going to be similar to what you might be seeing in your seat work. So let's try one here. Let's say we have a polynomial that is okay, and if they were to ask you to simplify this, all right, first thing you would do is look through it and say, okay, we have nothing but polynomials here. Nothing but polynomials here. So that's great. We can use our steps to simplify polynomials. And what's the first step? Well, we need to combine the like terms. Here, in order to do that, we kind of want to get rid of these parentheses. Okay, now, can we get rid of these parentheses? Can we just drop them? That would be the question. So this first set of parentheses, nothing from the outside is being multiplied by this set of parentheses. So that's good. The other thing is we don't have any negative sign preceding it. So if we had a negative sign over here, we'd have to distribute that negative through each term. But we don't have that. We just have an invisible plus sign. So this first set of parentheses are really unnecessary. We really don't need those. They just put those in there to make you work a little bit harder. So we will rewrite this problem without that set of parentheses. Okay, and then we reach this plus sign right here. Now, because it's a plus sign, this second set of parentheses can also go away. There's nothing on the outside being multiplied in to this set of parentheses, and this plus sign isn't going to change anything on the inside. All right, so we can just continue with this plus sign and just drop the parentheses completely and get 2x to the third plus 4. Okay, so all we did was drop the parentheses here. They were only placed there so that you had to think about it a little bit more and just validate to yourself that you can drop those parentheses without creating a problem. All right, so now let's look at this. We can now take our first step, which is to combine like terms. We have what for like terms here? We have an x to the third, or x cubed, and we have an x cubed over here. So we can combine those and get 3x cubed. Okay, we have an x squared here, and there isn't any other x squared, so he's all by himself. So we'll just add the 3x squared. And then we have this plus 2 and a plus 4. We can combine those and get a plus 6. And there we go. We've now simplified to the extent that we've combined all the like terms. The next step is just to write it in the proper form. And if we look at this one, it's already in proper form, which is awesome. So we only have one variable, the x. So we're going to write this expression in terms of x being reduced in its power, descending the powers of x as we go from left to right. So x to the third is the biggest, then x to the second is the second biggest, and then there isn't any x, that's the last one. So that is in descending powers of x. So that is our solution. All right, pretty easy stuff here. Okay, let's try another one here. All right, so let's look at this problem. And it is very good to, above all, first look and make sure that everything is, every term is a polynomial. And so if we look at each term individually, we can say, okay, yep, they're all polynomials. I don't have any negative exponents. Watch out for that. Remember, negative exponents, that makes it no longer a polynomial. So make sure you don't have any negative exponents. And everything else is, within the constraints of a polynomial, which all this looks good. Then we can go ahead and simplify. And the first step is really going to be to remove these parentheses if we can. So if we look at the first set of parentheses, again, there's nothing being multiplied into this set of parentheses. That's the first thing. The second thing is we don't have any negative sign in front of it. So that's good also. In that case, we can just drop the parentheses, and we're going to be left with 3x to the third plus 2x squared minus x plus 4. Okay? Just drop the parentheses. Now, we have this negative sign and this second set of parentheses. So if we are trying to drop the second set of parentheses, we would look at this and say, okay, well, there's nothing being multiplied in. That's great. However, we do have a negative sign in the front. And because we have a negative sign in the front, that negative has to be distributed through. That negative has to be distributed through to every term within this set of parentheses. Okay? So in order to do that, we just need to change all the signs for all the terms inside the set of parentheses. And once we've done that, we can drop the parentheses. So instead of a positive x squared here, we actually have a negative x squared. Instead of a negative 7x, we're going to have a positive 7x. Instead of a negative 5, we're going to have a positive 5. So very important that we distribute that negative through every term in the parentheses. It's not just a negative x, it's a negative set of parentheses, which means a negative everything in the parentheses. Okay? All right, so once we've reached that point, now we can simplify by adding like terms. So what like terms do we see here? Well, let's see here. 3x to the third, he's all by himself. We don't have any x's to the third after that, so it's just 3x to the third. And then what else do we have? We have positive 2x squared. Well, we have a 2x squared and we have a negative x squared. Those can be combined, and that's going to give us positive 2 and a negative 1 is going to be a positive x squared. And then we have our negative x, positive 7x. They can be combined. That's going to give us a positive 6x. And then lastly, we have these these coefficients at the end, a positive 4 and a positive 5. That's going to give us a positive 9. All right, so we've figured every one. We've taken every term into account. And now we have them laid out. Let's just make sure they're in descending order of x. And lo and behold, they are. X to the third, x to the second, x to the 1. So therefore, this is the simplification of this. Okay? Very good. Let's see here. I think that might be a good place to stop right there. Well, you know what? Let's have you do one on your own here first. So let's give you one here. What if I have... All right, why don't you go ahead and try to do this one on your own, and then we will do it together. All right, so let's see how you did. First of all, just a quick question for you. Taking just this first set of parentheses, what could we say about this this expression inside the set of parentheses? What could we call it? Just a quick quiz here. What would we call this inside here? Hopefully you said a trinomial, right? Because we have 3 polynomials. And this over here, we'd also have a trinomial inside the parentheses. So just as kind of a reminder, kind of think of those as you go through these. All right, now let's go ahead and work this out. So we want to get rid of the parentheses. In this first set, that's not a problem. We're not multiplying anything by it, and there is no negative outside at the front. So that's just going to be 2x squared plus x to the third. Okay? Second one, we want to get rid of the second set of parentheses. And to do that, yes, there's nothing being multiplied. However, we do have the negative sign. That needs to be distributed through, so all of our signs are going to change. So we're going to have a negative 4x, a negative x squared, and a positive 4x to the third. All right, that being done, we can add. So we look for like terms. I have a 2x squared and a negative x squared. That can be combined, and that'll give us an x squared. And then I've got, what else? I've got a positive x, and I've got a negative 4x. That's going to give me a negative 3x. And then I've got, whoops, we won't go that color. Let's go this one. We'll go a positive x to the third, and we have a positive 4x to the third. So those can combine, and we're going to end up with positive 5x to the third. All right. And then lastly, we want to look at this and make sure that it's kind of written in the standard form. And this one, in fact, is not. So we're going to write that with the x with the greatest power first. So 5x to the third would come first. Then we would go to that positive x squared. And then we would go to the negative 3x. So our x's are descending in power. 3, 2, and then 1. All right, so that would be our solution. All right, well, very good. I think that's about all there is to it, Luke. So it's a very simple lesson here. Go ahead and give the seat work a try, and we will continue tomorrow.